Hello and welcome to the Embedded C Programming Design Patterns course. This course is available here on YouTube, and also if you don't want to wait until the next module comes out, you can get this course as a book, as book plus videos, Udemy course, and also all of the book and video content, as well as live sessions with me on Wednesdays, which is available at swedishembedded.com. So the book is available on Kindle. You can download it from Amazon. The Udemy course contains the book materials as resources, as PDFs here. And on the website, we have the course available as a standalone course directly on the website. You just click join here, enter your details, register as a student, and then you will have access to all the course materials and also the weekly Q&A, which is in 5 days, 8 hours at the time when I'm recording this. All right, so let's get on with the next module of this course. Hello and welcome to another module of the Design Patterns training at swedishembedded.com. My name is Martin Schroeder, and if you have any questions, you can always join our Discord channel. You'll find the link at swedishembedded.com. There is a link in the corner. And if you have any other questions, you can always email me at martin.schroeder@swedishembedded.com. Today we're going to talk about the bridge pattern, and this pattern is primarily used to join two different hierarchies of objects. So we'll look at how we do that and how we can implement that in C and also in Rust. What are the defining characteristics of this pattern? This pattern is basically structured as a way of decoupling abstractions and implementations. So we have one abstraction on one side of the bridge, another abstraction on the other side of the bridge, and then the bridge is kind of joining those two together so that we can control the objects on the other side of the bridge through abstractions that we have on our local side of the bridge. And one way to understand this is to imagine that this is kind of a network connection. So you have one side of the bridge where you have normal object abstractions with which you interact, and then all of the calls kind of pass through the network, which would be the bridge, and then end up on the other side, on the server side, where the calculations actually take place and the operations are actually executed. And even if you don't have a network, as way of bridging those two hierarchies together, you can still have the same concept even in a monolithic application. So the last defining characteristic of this pattern is that it has two distinct hierarchies of objects that can evolve independently and that are connected using this bridge connection. There are multiple typical use cases for the bridge pattern, but all of them have one thing in common. You have a tight channel through which all of the API calls pass, and this is what corresponds to the bridge. So in the older 3D gaming, when there were multiple implementations of OpenGL and every graphics card vendor had their own implementation that was shipping with their graphics card drivers, the games that were using OpenGL, they had to resolve the OpenGL functions manually and have fallbacks in place so that they could still function when some of these functions were missing. So one solution to that was to implement a bridge between OpenGL, between the actual OpenGL drivers and the game itself. And this bridge was responsible for implementing those fallbacks. Another example is the Linux system calls, where everything is passing through a system call interface. And there are abstractions on both sides. So you have the C library is essentially an abstraction that represents the client side or the user space objects of the kernel. And any interaction with the kernel objects goes through the system call interface, and that is the bridge. And another example is plugin architecture, where you have, if we look at the older Quake games, the game itself was exporting an abstract interface, but this abstract interface was also a bridge because everything that the game did and every event that the game received. So the game was separate from the engine itself. So there was a game executable, or actually DLL, and then there was the game engine that was responsible for running the simulation of the game. And so any event that the user, that came from the user, for example, needed to be forwarded to the game was going through this interface. And that was also a bridge which allowed the game engine to evolve separately from the game itself, and both of these sides had their own hierarchies of objects that communicated through the very lightweight and generic interface which corresponded to the bridge. And based on these use cases, you can kind of see already right now that the bridge pattern is for cases where you have large hierarchies of objects. You shouldn't be misusing the bridge pattern for small interfaces between objects, because it doesn't really make sense at that level. Some of the benefits of the bridge pattern include that you get a very clear way of separating two hierarchies, and you have full control over everything that passes between one hierarchy and the other. So you get a kind of a insight and overview over the communications between those two hierarchies. And the bridge pattern is essentially for simplifying the interface between one hierarchy and the other, and kind of connecting those objects without actually having to derive or contain the implementation of the other object. On, let's say, for example, you have a server-side object and a client-side object, and they're connected through the network bridge, and you don't need to instantiate the server-side object directly in the client-side object. You have this abstract interface that connects the two objects together. So they're essentially, they don't even need to be on the same machine. So that's one of the benefits. This complete separation is one of the key benefits of the bridge pattern. And we also get dependency separation, because now the both sides of the bridge can have their own dependencies that are completely independent from each other. And also separation of concerns. The bridge pattern, by definition, enforces the separation of concerns, because those two hierarchies, they kind of have to exist on their own. And they need to pass all of their messages through the bridge itself. The main drawback is, of course, increased complexity, because now you need to design this interface of the bridge, and you need to have a lot of additional code that is only there to implement the pattern. So the bridge pattern is, it only makes sense when you have this requirement of completely separating two parts of your application. For example, you have the game engine and the game, you have the client and the server, you have the kernel space and user space, you have the game and the driver that comes from the manufacturer that needs to implement the OpenGL API. So when you have this very clear need to separate two things, that's when it makes sense. Because the drawback is that it's going to be more complex, and it's going to have additional indirection, and it's going to take more time to develop. Let's look at the implementation now. We're going to use an example. We're going to use the client server as example, and we're going to look at the implementation both in Rust. So we're going to start with the Rust implementation, and then we're going to go to a C implementation. And this is the first time I mentioned Rust in this training, at least in this current version of the training. So this is going to be an interesting aside from the other modules of this training, where you can kind of see the mapping between how we do things in Rust and how we do things in C, and how those two worlds correspond to each other. So we're going to have a client-server model. We're going to have two hierarchies of objects. We're going to have the client responsible for drawable, basically the visual representation of an object, and the server is going to be responsible for the physics representation of the object. Of course, we're not going to go ahead and implement all of those things in detail. We just kind of have the conceptual objects that we're going to interface together and build a bridge between. And the user is going to interact with the client-side object. So the user is going to just view the client-side object, and then everything else is going to just happen automatically through the bridge implementation underneath. So let's create our server-side objects. So we're going to use Rust for this, and we're going to define a server-side circle and a square. And then we're also going to define the position of this object, which is going to be represented by point2d, which is basically a struct that has two anonymous fields. This is a way to define a struct that is basically a tuple. And then we're going to implement a simple circle that just creates an empty object, and a simple square that also creates an empty object. In Rust, we use the impl keyword to create an implementation like this. And then we're gonna move on with the physics objects interface. So we're gonna create a trait, and in Rust, traits are basically one of the core types. So you can actually explicitly define a trait using the Rust syntax. So we're gonna implement a trait that has a position method, and it's gonna return a point to D. So this method is basically designed to return the position of the object that implements this trait. And then we're going to implement this trait. So we're going to type implement physics objects for circle, and then we're going to have the implementation of this function. So we are returning a point to D, and then we're just going to return hard-coded values just for the sake of the example. And we're going to also implement this trait for the square. So now we have two virtual methods here that give us position. Basically, we can treat these two objects, circle and square, the same way by referencing the trait. So we can use the trait object to interface with these two using the physics object trait to get their position. And the client-side objects then are going to be implemented as structures on the client side. So we're going to have a circle that has that is a parameterized type, so it's a template basically, and it's going to use the physics object server interface. So this is a trait, right? So this is the abstract interface to the server-side object, and then we're going to have a circle and we're going to have a square, and it's going to have this member called physics, which through which we're going to get the position of the object, and it's on this physics object interface, that is the part that can be swapped out for a network bridge, for example. So we can essentially replace the way that we interface between those two hierarchies, and we can do that without having to modify the rest of the code. And then we're going to have a implementation for this circle and the square. So this is corresponding implementations on the client side. And then we're going to implement a drawable trait. So this is a trait that is only present on the client side. So here we're going to have a drawable. It's going to have a draw method, and basically both of these objects are going to implement drawable trait for this parameterized type of physics object. So now we have two draw methods, and we can now interact with these two different types in the same way using the drawable trait. And now we can use this very simply by creating a drawable. So we're gonna create client circle new, and we're gonna also create an interface to the server-side object so that we get so that we can pass this server-side interface to the circle and square new method. So if we look at the definition here of the new method on the client side, the new method takes a parameter which is assigned to the physics interface to the object, right? So we have a physics, and this is a trait. So when we create this circle new, we basically assign a trait here. We pass it to the client-side circle constructor, and then we get a client-side object with which we can interact. And now, when we call this generic interface on the client side, then the server-side interface of the physics object is also going to be called, and this is how we can connect the two hierarchies together. Now let's look at the implementation in C. So the C implementation is by default more verbose, so it involves more typing, but this is basically the same implementation as we just did in Rust, but now we're doing it in C. So we're going to define our structure for the point 2D. We're gonna, in this case, we're gonna use integers. We might as well use floats, but I decided to use integers for the example. Then we're gonna implement the physics object trait. So in this case, in C, we implement traits as a struct, and we're gonna have one method, position, which basically takes the pointer to pointer. Look at the virtual API pattern to understand how this works. And then we're gonna have a physics object handle defined here, and we're gonna have physics object position method, to basically a generic trait method to get the position. Then we're going to have a server-side object. We're going to have a server circle, and server circle position gets the position from the server, and we have the circle ops here that is the instantiation of the trait, and then we assign this instantiation of the trait to the internal ops parameter here, which is a const struct physics object ops that represents the operation for the server-side circle. So basically, this is the trait implementation for the trait representation for physics object for the server circle struct. Then we have the server-side square implementation, which is basically the same thing, but now we have a square, and it has its own implementation of the position, just to differentiate the two types. And then it also has a trait implementation for the physics object ops, which is assigned in exactly the same way. And now we go to the client-side implementation. So we have our drawable interface, and we define the trait drawable with a single draw method. And then we define the handle, and we define the generic drawable draw method. And we can then continue to the client-side objects. We have our client circle, which has the physics object T, server object trait, basically an interface to the server object. And this is where we would implement the bridge. So we could have an implementation of the server-side object that would actually pass the calls through a network API. This would be the interface for our client-side circle. We then have a draw method. This is the local interface for drawing the particular circle. And we then also do the same thing for the square. So we have our client-side square, which points to the server object for the square. And then we basically implement the trait for drawing a square, right? And our constructor, just like in Rust, it takes the physics object trait for the server side of things, and also it takes the self pointer, because in C we don't have a default self pointer as we do in Rust. And the usage is very similar to how it's used in Rust. And notice how much the code is simplified when it comes time to actually use this code in practice. So for the usage, we instantiate our server circle and server square, and we instantiate the client circle and client square. We initialize both of them, and then we just call the drawable draw. And the drawable draw is then going to call the server side interface to get the position of the object. So that's how we implement the bridge pattern in Rust and in C. It's pretty simple. The complexity is it's basically mainly in designing this abstract interface or multiple abstract interfaces that correspond to this bridge pattern. Some of the best practices for implementing this pattern: identify the component hierarchies that need separation. So don't implement this pattern for just any type of object. Use the concept of hierarchies. So try to separate things into two different hierarchies, and then define clear interfaces that are going to be used for the bridge, and then implement the bridge pattern. And also have thorough testing, because testing is going to be your primary way of identifying misbehavior on part of the implementation objects. So you want to be able, you want to have tests in place that verify that your implementations actually correspond to the requirements of the abstract interfaces that you're implementing. Some of the pitfalls is over-engineering, using this pattern too much. It's a complex pattern, so if you use it for a lot of different objects in your software, you're going to have a lot of maintenance cost that comes with it, because you have a lot more objects that are just there to provide this path of data between one side and the other side. And also another pitfall is having the interfaces that are too complex. So keep your interfaces simple. The Linux system call interface is a simple interface which is used by all the client-side applications to interact with the system. So there is a lot of complexity on both sides, but the interface itself is simple. So don't make the interface complex. That's another big pitfall with this design pattern. Some of the alternatives to this pattern include adapter pattern. So this pattern is a lot more lightweight, and it's primarily used to adapt from one interface to another. But it's also not the same as the bridge pattern. Another pattern is the strategy pattern, where you have different behaviors that you swap out. And it's also not quite the same as the bridge pattern. So bridge pattern is pretty much the main pattern you would use if you have two hierarchies that need separation and a connection between them. But nonetheless, those are some alternatives that you can also look into. All right, so in this training, we have covered the bridge pattern. We have looked at how we can implement the bridge pattern in Rust and in C. There is an example for this in the Swedish Embedded Platform SDK. There is a link in the corresponding PDF file that is also part of this module or in the actual written content that comes with this video. We have looked at some of the pitfalls and best practices of the bridge pattern. So hopefully now you have full understanding of the bridge pattern, when you should use it and also when you shouldn't use it. So let's verify your understanding of this pattern. What is the main defining characteristic of the bridge pattern? How does the bridge pattern decouple abstractions and implementation? What underlying pattern do we use as part of the bridge pattern that the bridge pattern kind of builds on? What is the role of abstraction in the bridge pattern? Why do we need to have those extra abstractions? What are we trying to abstract away? What is the main difference between the bridge pattern and the simple abstract interface? And lastly, how can you use this pattern to simplify your current architecture in the projects that you're working on? That's it for this training. I hope you learned something, and I'll see you in the next module.